Welcome to the presentation of our paper, Test Time Adaptation for Video Highlight Detection using Meta-Auxiliary Learning and Cross-Modality Hallucinations. Over the recent years, we are seeing a tremendous growth of video data over the internet. It now consumes around 73% of internet traffic. So, to manage and curate this vast video content, we need effective automated methods. Our paper deals with one such method, video highlight detection, which automatically identifies and extracts key moments from a long input video. It is helpful for video navigation, recommendation, editing, and searching. In this figure, we show an example video from a video highlight detection dataset. The moments with green border are marked as highlights by the users or annotators. These moments can be stitched together to form the video highlight. In this work, we tackle a key limitation of existing video highlight detection methods. These methods use a generic fixed model that do not adapt to unique characteristics of each video, such as their diverse content, styles, and audio and visual qualities. Besides, despite the potential of audio cues for indicating video highlights, they remain underexplored. Our goal is to develop a solution that dynamically adapts video highlight detection models to new unseen test videos with diverse content, styles, or audio and visual qualities. We propose Highlight-TTA, a test time adaptation framework for video highlight detection that adapts to variations in test videos. We propose to use meta-auxiliary training scheme for optimizing model parameters while ensuring efficient adaptation. We also utilize cross-modality hallucinations as a self-supervised auxiliary task and demonstrate the benefits of leveraging audio alongside visual cues. We demonstrate the effectiveness of Highlight-TTA with 3 state-of-the-art highlight detection models on 3 benchmark datasets. We use a self-supervised auxiliary task in our framework. In machine learning, auxiliary task basically means an additional task that is trained alongside the primary or main task that we want the model to learn. The goal is to enhance the performance of the primary task by adding or providing additional supervision and learning robust feature representations. For example, in image classification, classifying images into categories is the primary task, and learning to predict image rotation angles alongside the primary image classification task can be considered to be an auxiliary task. For test time adaptation, self-supervised objectives are used as auxiliary tasks, and they are used as ground truth annotations are not available for test data. We use a self-supervised task called cross-modality hallucinations. We use this auxiliary task to adapt our model to each new unseen test video and use the adapted model to detect highlights of the video. The naive approach of introducing an auxiliary task with a primary task can be called joint training, as shown in this figure here. Here, you calculate the primary and auxiliary task in the same forward pass and backpropagate at once using both losses. However, it has shown to be suboptimal as it can be biased towards improving the auxiliary task at the expense of the primary task. Hence, we employ a meta-auxiliary training strategy based on MAML meta-learning algorithm. MAML was proposed for fast adaptation and few-shot learning. It tries to find an initial model that can be quickly and effectively fine-tuned or adapted to do new tasks. MAML does this by optimizing and updating initial model parameters based on the performance of the fine-tuned model on new tasks. On the other hand, our meta-auxiliary training strategy tries to find a model that can be effectively adapted to new unseen test videos so that it can be utilized for test time adaptation. During training, we optimize the initial model based on the performance of the adapted models for each given test video. This ultimately obtains a model that is highly adaptive to new unseen videos. To introduce Highlight-TTA framework on top of highlight detection model, we add 2 lightweight hallucination modules as shown in the figure on the right. These 2 modules are used to perform our auxiliary task called cross-modality hallucination. In cross-modality hallucination, the objective is to approximate or hallucinate features from one modality, such as video, given the features from the other modality, such as audio. The first hallucination module on the top hallucinates audio features using the visual features, and the second module at the bottom hallucinates visual features using the audio features. The cross-modality hallucination losses are calculated by comparing the hallucinated features with the actual features using mean squared error loss. We use this meta-auxiliary train model for test time adaptation during inference. At test time, for each given test video, we first update the model using the auxiliary task. This adapts the model specifically to the given test video. Next, the adapted model is then used to detect highlights for that given test video. Here is our meta-auxiliary training algorithm. Our algorithm has two nested loops, inner loop and outer loop. For each given video, in the inner loop, we first adapt the model to the given video with some gradient steps using the auxiliary task. Then, in the outer loop, we use these adapted models to perform our primary highlight detection task. The gradients from the primary task are backpropagated through the adapted models to optimize the original model. This ultimately obtains a model that is highly adaptive to new unseen test videos. We implement our Highlight-TTA framework on top of three state-of-the-art highlight detection models, JAV, UMT, and QD-Dator. All of these models are either attention-based or transformer-based models. We use three datasets, YouTube, TVSum, and QV highlights. The YouTube dataset is collected from YouTube videos and have videos categorized into 6 categories. TVSum contains a diverse set of videos from 10 categories. QV Highlights is the largest with about 10,000 videos, and it requires submission to an online evaluation server to obtain the results on their test set. We use standard evaluation metrics used by existing video highlight detection methods. They're mean average precision, top 5 mean average precision, and hit ratio. Mean average precision is a popular ranking quality metric that considers the number of correctly detected highlight clips and also their ranks or position in terms of their highlight scores. Top 5 mean average precision only considers the top 5 clips with higher predicted highlight scores, whereas hit 1 only considers whether the clip with the highest predicted highlight score is actually included in the ground truth highlights or not. Next, we present some experimental results. On the TVSum dataset, with the introduction of our Highlight-TTA framework, we see a good performance boost. Similarly, on the YouTube dataset, we also see a noticeable performance gain with the introduction of Highlight-TTA. We see a similar improvement on the QV highlights dataset as well. Now, we present some qualitative results. The video on the top shows a man surfing, and the video in the bottom is a vlogging video. We show the highlight annotations using the green borders and the yellow regions. The blue regions indicate the highlight scores predicted by our model. The red lines indicate the predictions of the simple joint train model. We can see that Highlight-TTA framework improves the alignment of the predictions with the ground truth much better. We conduct several ablation experiments. Here are some selected ones. In this ablation experiment, we analyze the individual and combined impact of meta-auxiliary training and test time adaptation steps. We can see the combination of these steps as proposed in our Highlight-TTA framework achieves the best performance. Next, we implement several existing state-of-the-art test time adaptation methods by modifying them for video highlight detection tasks. We compare their performance with our Highlight-TTA framework. Highlight-TTA outperforms these methods while maintaining comparable or lower GPU memory consumption and similar inference times. To conclude, we address video highlight detection task, which aims to identify the most important or engaging moments in a video. We propose Highlight-TTA, a novel test time adaptation framework for video highlight detection. It dynamically adapts the video highlight detection model during testing to better align with the specific characteristics of each test video. It leverages cross-modality hallucinations as an auxiliary task and incorporates meta-auxiliary learning. The results underscore the potential of test time adaptation in advancing various tasks, including video highlight detection, and open up avenues for further research in this domain.